Video is about contraction of skeletal muscles as a whole. Make sure you print out the PowerPoint for Muscles Part 3 so you can fill it out as you're watching this video. So far, we've been focusing on skeletal muscle at the cellular level and how it works at this level. But we're going to take a step forward now and take a look at muscle as a whole. Just a quick review. Remember that a motor unit is one motor neuron and all the muscle cells it stimulates. Motor units can be small or large. A small motor unit would be one motor neuron just stimulating a few muscle cells. So in this case, let me give you an example of this. This might be, for example, the eye muscles. So when we get to this point, you'll find that the eye has these 6 tiny strap-like muscles around it. And each muscle is very small, and it only is made up of small motor units. So what this does when you have a small motor unit is it doesn't produce a lot of force, but it actually gives you a lot of precision. Precision is how much control you have over that muscle. So again, a small motor unit is one motor neuron stimulating just a few muscle cells. Another example would be the intrinsic muscles of the hand. Now remember, intrinsic means within. So these would be the muscles that are actually physically in your hand. These are also small muscles controlled by small motor units. On the other hand, a large motor unit is when you have one motor neuron which stimulates several hundred muscle cells. And an example of this, I'm going to put it down here, would be the gastrocnemius. And you don't perhaps know this muscle yet, but this is the posterior lower leg muscle, the gastrocnemius. This is a C right here, by the way, C. So this is a fairly large muscle, and it has large motor units, several large motor units. So what you get with large motor units is you get a lot of force because many muscle cells are contracting, but you don't get a lot of precision. That means you don't have a lot of control over these muscles. When you look at any one muscle, usually there are several motor units throughout the muscle. And when you only have a single motor unit contract, you get a very weak contraction. So let's look at how muscle cells versus whole muscles respond to an action potential or nerve impulse. When a single muscle cell receives an action potential, you have what's called an all or none response. That means either the muscle cell contracts or it doesn't contract. On the other hand, with a whole muscle, you don't have an all or none response. You don't have either the muscle contracting or not. You have instead what's called a graded response. And a graded response is actually a range of responses of the whole muscle. From weak to strong. Okay, so a range of responses of the whole muscle from weak to strong. This means that the muscle can produce a small amount of force, perhaps the amount of force that you need to produce to lift your textbook, which is about 5 pounds, or it can produce a lot of force, maybe 150 pounds worth of force to lift a 150-pound barbell. So a graded means a range, and a whole muscle is able to do that. And we actually need to be able to do that for proper control of skeletal movement. So how does the body produce a graded response? Well, in a graded response, 2 things are happening. First, you change the frequency of the nerve stimulation. Now, when we say nerve, what we're really talking about nerve stimulation is action potential. And frequency means how fast. So you can produce a graded response by changing how fast the action potential arrives at the muscle. The other thing that happens is the number of motor units are changed. So you change the number of motor units stimulated. Now, both of these things are necessary to produce a graded response. The first one provides a smooth muscle, a smooth movement. The second one results in a change in force. So let's look at how changing the frequency of the muscle stimulation of the nerve impulse affects the muscle. So if we have a single stimulus of a motor unit, it results in a single brief contraction. And this is called a muscle twitch. And I'm sure all of you have had twitches before. The muscle is just contracting and relaxing. It is a simple contraction observed on a myogram. A myogram, we're going to take a look at this in a minute, but this is a graph of the force produced by a muscle as it contracts. And you can see again this prefix here, myo. Remember, that refers to muscle. So again, this is a graph of the force produced by a muscle. In a muscle twitch, it is not a productive event. That means it doesn't produce enough force to really lift a load, to really do something of value. So think of a muscle twitch almost as a mistake. And this is what happens again when you have a single action potential. So let me give you an example about the frequency here, because we're talking about frequency of action potential. So in an active muscle, so this could be a muscle like your biceps brachii, which is in your upper arm, which helps you lift things. Usually you have an action potential every 1 to 2 milliseconds. Okay, so an action potential is arriving about every millisecond. But when you have a twitch in a muscle, you're getting an action potential every 20 to 200 milliseconds. So you can see how the action potential is arriving a lot slower. And what happens is the muscle contracts and relaxes, but it doesn't really produce enough force to do much. So let's look at a myogram. And here's a myogram. You'll notice on the x-axis down here, we have time in milliseconds. Remember, there's 1,000 milliseconds in a second. So you can't even say millisecond in a second, in a millisecond. And then up here, you have tension in grams. And think of this as the amount of weight that you're moving, or the amount of force that's being produced. So here we have a single stimulus. This means a single action potential. And you can see that the muscle contracts and relaxes. And if you look at the force, there's not that much produced, because up here is a lot of force. So very little force produced, not enough to do any helpful work. If we look closely, now let's increase the speed of the action potential. So now what we're going to do is, I'm just going to give you an example. Let's say the frequency of the action potential is 10 to 20 action potentials per second. So every second we're getting 10 to 20 action potentials. And so let's take a look here. So again, we have time on the x-axis, tension on the y-axis. The green arrow is an action potential. So what happens is you get an action potential, the muscle contracts, the muscle relaxes. Another action potential, contracts, relaxes. Another action potential, contracts, relaxes. Now what you might notice as we move along here, is that the amount of force that's being produced is increasing. This is called treppe. Treppe is when you get an increase in force with every successful action potential delivered. And what's happening here is that each contraction produces more force. And that is because when a action potential occurs, remember that calcium is released, it binds to troponin, troponin pulls tropomyosin off the binding sites, myosin binds to the thin filament and it pushes it towards the center. The sarcomere, the myofibril contracts, the skeletal muscle contracts, the whole muscle contracts. But then when it's done, the calcium has to go back to the terminal cisternae of the sarcoplasmic reticulum. It's got to go back. But when the frequency is this quick, there's not enough time for the calcium, all of the calcium, to go back to the terminal cisternae. So a lot of it is still floating around in the cytoplasm. What this means is that the next time you have an action potential, there's more calcium in the cytoplasm, which means that there's more force, because the more calcium, the more it binds to troponin, the more troponin molecules pull off tropomyosin, the more force. The other reason why the force increases with repeated action potentials is that you're heating up the muscle. And as you heat it up, you increase the efficiency of ATPase. So remember, ATPase is an enzyme that's responsible for the hydrolysis of ATP. So the more efficient it is, the more ATP is hydrolyzed, the more energy the muscle is able to produce. So what's going on here is the frequency is still fairly slow, even though it might not seem that way, 10 to 20 action potentials per second. But what happens is, because it is at the speed it's at, there's not enough time for the calcium to be reabsorbed into the terminal cisternae, and so each successful contraction is stronger. This is treppe. Now, when we're doing a sustained activity like running or playing tennis or swimming for 30 minutes, this is not what's happening in your muscles. So let's go on, and now we're going to increase the frequency of the action potential a little more. So now the frequency is going to be 20 to 30 action potentials per second. Okay, so remember, it was 10 to 20 and we had treppe. Now it's 20 to 30. So you'll notice here the green arrow, an action potential. The muscle begins to contract, then it begins to relax, boom, another action potential. So now the muscle's still partially contracted, and it begins to contract again, and then it relaxes, boom, another action potential. So it's even more contracted when the next action potential comes along, and it contracts even more, boom, another one. So what's happening is every time there's an action potential, more and more contraction occurs and more force occurs, because the muscle never gets to go all the way back to its original resting length. So it's already partially contracted when the next action potential arrives. And this tends to form these waves, and they call this wave summation. And what's happening here is the force is increasing. Now, believe it or not, this is still not what your muscles are doing when you're doing a sustained activity. This is too slow. So let's increase the frequency a little bit more. And in this picture, the frequency is going to be about 30 to 40 action potentials per second. All right, so now we're speeding it up. Again, action potential, muscle starts to contract, begins to relax, boom, another one. So we're seeing what looks like wave summation, but we've sped it up. So the action potential is arriving quicker, and what happens is eventually you get to some force, which is the force that you want your muscle to produce. So for example, if you are running, it's the force produced, let's just look at the gastrocnemius, which is the posterior calf muscle. You end up producing enough force to move the leg. And once you get to that point, you don't need to produce any more force. So they call this incomplete tetanus, and it produces the force required. Now you'll notice up here that it's not the maximum force that this muscle can produce. It's not the maximum. It's just the amount you need to do this particular activity. And this is what almost all the time our muscles are doing, no matter what activity they're doing. This is the most common type of response, graded response you're seeing. Now, I will say that if we look at the gastrocnemius, which is a big muscle, there are multiple motor units. And so what's happening is some motor units are doing incomplete tetanus. So some motor units are being stimulated while the others are resting. And then when the ones which are being stimulated are done, they rest, and the ones that were resting, they contract. So it's almost like the motor units are taking turns. And what they call this is asynchronous contraction of motor units. Asynchronous contraction of motor units. Asynchronous means not at the same time. So again, what usually happens in typical graded responses when you're doing exercises that are sustained is that some of the motor units in your muscle are contracting. They're going through incomplete tetanus while the other ones are resting. And then they switch. The ones that were active, they're resting. The ones that are resting undergo incomplete tetanus. And you produce the force that you need for a long period of time. So that's typically is what's going on in your muscles. Now let's look at an extreme situation where we increase the frequency of the action potential even more to about 40 to 50 action potentials per second. If you look at the graph now, what you're seeing is the action potential arrives, the muscle starts to contract, but before it can even relax, there's another one and another one. So what happens is the force keeps building and building and building until you meet the maximum tension or force that that muscle can create. And they call this complete tetanus. Now, complete tetanus is very rare in humans, in living organisms, because if you think about it, in complete tetanus, all of your motor units must be contracting at the same time, because that's what has to happen if you're going to produce a maximum tension. If they're all contracting at the same time, then they all have to relax at the same time. And if these were the muscles of the leg that we were talking about, you would collapse. So people don't do complete tetanus when they're doing exercise. There are extreme situations sometimes where they do that, but mostly when you see complete tetanus in a muscle, it's being artificially stimulated by an electrical impulse. So again, we're talking about the graded response, and we said that the two things that happen during a graded response is you change the frequency of the nerve impulse, which we just finished talking about, but the other thing you do is you change the number of motor units stimulated. So muscle force depends on how many motor units or skeletal muscle cells are contracting. The more muscle cells that are contracting, the more force. And that's pretty straightforward. So this action where you're increasing the number of motor units that are stimulated is called recruitment. So think of it this way. If you have an army and you want your army to be more powerful, you recruit more soldiers. If you're a muscle and you want to produce more force, you recruit more motor units. That just means you stimulate more motor units. And as a result, more muscle cells contract. So both of these things happen during the production of a graded response. You are changing the number of motor units that are stimulated, and you are changing the frequency of the nerve impulse. So let's take a look at this picture, and we're going to focus on this bottom one for a sec here. So you'll notice at the top, these round things are supposed to be a muscle. Okay, so this is a muscle. The little tiny round circles are supposed to be motor units. And when it's a light color, it means the motor unit is not stimulated. When it's a dark red, it means the motor unit is stimulated. Directly below it is a myogram, and you can see time on the x-axis in milliseconds and tension on the y-axis. So if we look above to the first muscle, you'll see that none of the motor units are stimulating. So if you look at the graph, there's no force generated. And again, in the second muscle, no motor units are stimulated, no force. In the third muscle, 2 motor units are stimulated. And you can see down here, a little bit of force is produced. And then in the fourth muscle, we've got 1, 2, 3, 4, 5 motor units stimulated, a little more force. So as we go along, the more motor units that are stimulated, the more force is produced, until at some point, we're at the maximum force produced by that muscle. So my question is, why can't we produce more force here? Well, the answer is above. You can see because every single motor unit is stimulated. There's no more motor units to stimulate. There's no more muscle cells to contract. They are all contracting. And this, of course, would be an example of complete tetanus. Okay, down to some more practical issues. If you've ever gone to the gym, you might have heard personal trainers using the word isotonic and isometric. So what does that mean? An isotonic contraction is when the muscle changes in length and moves the load. So for example, if you have weights around your ankle and you're sitting down and you raise your lower legs, then the muscle is changing length and you're moving the load. So you might think, well, isn't that always what happens? The muscle contracts and you get movement, but not always. Isotonic contractions can either be concentric or eccentric. Concentric isotonic movements are when the muscle shortens and does work. So think about picking up a dumbbell off the floor with your arms. So as you lift it up, okay, you're going to do flexion here of the forearm. As you lift it up, the muscles in your upper arm are shortening and you are moving the load. That's called isotonic because the muscle changes in length, and concentric because it's shortening. So isotonic concentric contraction is when the muscle shortens. Now on the other hand, let's say you have that barbell and you've got to put it down on the floor, but you can't drop it. You have to lower it slowly. Now you're doing flexion of the forearm. So in this case, the biceps are lengthening, but they're still producing force because you're holding up the muscle. This is called eccentric. So this would be isotonic eccentric contraction. So let's take a look here. And this is going to be isotonic concentric. So here we have a muscle, and it is attached up the top here. And at the bottom part, you've got a 3 kilogram weight on it. So it's stretched out. Then we're going to stimulate the muscle, usually with an electrical impulse. And you can see the muscle shortens, and it moves the load. So isotonic because the length changes, concentric because it shortens. Okay, and I'll let you look at these graphs on your own. It's just showing you what happens with isotonic concentric. But let's look at the next one, which would be isometric contraction. So in an isometric contraction, the muscle is producing force. However, it is neither shortening nor lengthening. So this is strange. The muscle is not shortening or lengthening. It is producing force, but it is not moving the load. And that is because the load is greater than the force the muscle can generate. So think about it. There must be some weight, some barbells that you cannot lift, right? Maybe 200 pounds. You cannot lift 200 pounds. Your muscles just cannot produce that much force. So if you try to lift 200 pounds, your muscles are generating some force. The thick and thin filaments are trying to slide past each other, but they can't. There's a little bit of movement, but not a lot. If you were to look at, let me give you an example. So here's a muscle again, but now we're attaching 6 kilograms. And we're stimulating it with an action potential, and it is producing force, but it just can't shorten. So again, the thick and thin filaments are sliding past each other, but they can only get so far. They can only get so far. So let's take a look at this graph now. On the top, on the y-axis, is the tension produced in kilograms. Now remember, 6 kilograms up here, that's the force we have to produce to move the load. On the bottom, the x-axis is time in milliseconds. So you can see that the muscle is being stimulated and it is producing force. More and more and more motor units are being recruited, but you don't have enough motor units to produce 6 kilograms of force. So it just levels out at that and then it relaxes. This graph on the bottom has muscle length as percent of resting length. So at 100%, it means the muscle is totally stretched out. It hasn't shortened at all. And then here it would be 90% of the resting length, 80, 70. So you'll notice here's the nerve impulse, and the muscle is beginning to produce force. However, it is not shortening at all. So what this is showing you that even though the muscle does not shorten at all or lengthen, force is being produced, but not enough to move the load.